In this video, we're going to be going over an example related to shear stress and rectangular beams. I'll let you pause the video so you can read over the question and attempt the question on your own if you want. So, in the question, we have a rectangular beam with a point load of 6 kips at midspan of the beam. We're told to find the shear stresses at points H and K at section AA of the beam. The equation that we'll be using to find shear stress is tau equals to VQ over IT. We have to determine each of these values to find the shear stress, so we'll start with finding V, the shear force. To find shear force, we can find the reaction forces at A and C, and then use the forces to draw a shear force diagram. From the shear force diagram, we can see that at section AA, the shear force is 3 kips, which is also equal to 3,000 pounds. The second value that we want to find is I, the moment of inertia, which is equal to base times height cubed divided by 12. And we'll get 1,687.5 inches to the power of 4. The next value that we're going to find is Q, using H as our point of interest. So when we draw a quick diagram of where we're measuring to, we'll need to take the area of this hatched shape. So the area of the shaded shape is 6 inches times 3 inches, and y prime bar is the distance from the neutral axis to the centroid of the shaded shape, which is 15 inches divided by 2 minus 3 inches divided by 2. So Q with respect to point H will be equal to 108 inches cubed. The last value we have to find is T, the thickness of the section at point H, which will be this dotted blue line. So the thickness will simply be 6 inches. Now plugging all our values into the shear stress equation, we get that the shear stress at point H is equal to 32 pounds per inches squared, which is also 32 psi. Now let's find the shear stress at point K and figure out which values are the same and which are changing. So at section AA, the shear force is the same, which is 3,000 pounds, and the moment of inertia will also stay the same because it doesn't depend on the point of interest. So that will still be 1,687.5 inches to the power of 4. In some cases, T may also change, but in this example, we can see that at point K, the thickness is still 6 inches. The only value that changes is Q. So let's find Q with respect to point K. So at point K, this will be the area that we need to find, and y prime bar will be 15 inches divided by 2 minus 1 inch divided by 2. And we'll be left with 42 inches cubed. Note that when you're calculating Q, you can also use the area above point K. Let's quickly go over our calculation for Q, but with the shaded area in green. The new area of the shape will be 6 inches times 14 inches, and our y prime bar will now be 15 inches divided by 2 minus 14 inches divided by 2. And we'll get a value of 42 inches cubed, which is the same as the value above. So it doesn't matter if you consider the area above the point of interest or below the point of interest. For practice, you can go ahead and calculate for Q with respect to point H using the area below point H, and you'll see you'll get the same answer, which is 108 inches cubed. Now we plug in our values into our shear stress equation, and we'll get that at point K, the shear stress is 12.4 pounds per inches squared. To summarize our answers, we'll get a shear stress of 32 psi at point H and 12.4 psi at point K.